Our second session will begin. It has the same topic, circular research in AEC industry, and we will start with Professor Hayriye Eşbah-Tuncay from ITU. And her topic is focused on nature-based solutions for urban runoff, a circular design approach. And the moderator of this section will be Professor Elma Durmisevic.
Okay, you take this because he already announced you. Yes.
Evet, şimdi başlayalım. Çok teşekkür ederim. Thank you very much for inviting me to this very exciting topic. And then I will be bringing landscape design point of view to the built environment perspective. I'm a landscape architect. Hayriye Eşbah-Tuncay from the Landscape Architecture Department of ITU. I dedicated quite a big chunk of my career into nature-based solutions. For some reason, I cannot control the presentation. Okay. Anyway, today I will be talking to you more about the urban runoff side. And I'm sure you have experienced this heavy rains for a few days now. And it's a general thing. We have been looking forward to it for a long time. It was really dry summer in Turkey, and then we had finally a season coming with the rain. But as soon as rain comes, all the Turkish cities are dealing with the disaster situation these days. When you turn on your computers or on your TVs, there is a news constantly explaining how the cities of Anatolia suffered from the recent floods. It's only like a couple of drops of rain for 2 days, and then all of our cities are paralyzed by that. So that means we need to be really sensitive about these climatic issues, the extreme weather conditions, and then the actions that we need to take should be more of the nature-based if we want to adapt to the real conditions of the weather coming with this. So the World Economic Forum explains us that the most dreadful situations involving the risks of landscape, including the extreme weather, climate action failure, natural disasters, and biodiversity loss around the world. So that is giving us a kind of a signal for the future. And then they are also projecting for the future for 10 years, for the next 10 years, the severity over the short and long term will be coming from the failure to mitigate climate change again. And then if we fail to adapt to the climate change, that is proposing another threat, the second severe threat to our life or well-being as the creatures of Earth. So therefore, the sustainable goals, the sustainable development goals emerged, and 7 of these 17 goals specifically relies on water, and then the quality of the water, circular utilization of the water, and then the amount of water. The water is important in the public realm, and creating a water-sensitive cities is critical for the urbanism, climate, and water trajectories. And it is an imperative to deal with the climate crisis in the 21st century. What you are seeing in the middle as a picture is the street that I walk by every day to go home. This is a sunny summer day with all the begonias, the flowering shrubs are opening their wonderful face, and then this is a wonderful selfie spot. But as soon as the rain comes, this is the scene that we all have to suffer, or we all have to deal with as the habitat of this environment, of this built environment. So what we are seeing over here is a rainy day. And what we are also watching is wasting of the resource, wonderful resource and incredible commodity in the urban environment, which is the water, rainwater. So what we are also seeing here is great infrastructure that the cities, the modern cities of not only Turkey but all around the world rely on for many centuries to solve their runoff problems. But again, considering the situation coming with the climate change, the climate crisis, and how the water is a scarce commodity these days, we need to see what's going inside of these graves as the resource and then reverse this cycle so that we can reutilize this water again and again in a circular way in the urban environment. This is important because cities are complex systems, and then where the natural and built environment is in harmony, social, physical, and the other types of conditions support each other in the city, and therefore creating a sustainable city also depends on understanding the water and its relationship with the water, and living in a healthier environment always creates this prospect, progressive environment in terms of the economy and social and ecological relationships. So therefore, with the increasing effect of climate change and heavy and sudden rains and long-term droughts affecting daily life and the economy more than ever, cities has to change their approach to the water, becoming more on the less on the gray side, but more on the nature-based and green side. So some of the countries around the world has already developed their own scheme regarding the utilization, circular utilization of these urban runoff in a more sustainable and nature-based. And then they all gave their significant titles to this gesture of living with the sensible, being sensible with water. So, for example, in China, it's called smart city. In the United States, it's called low impact development. In the British sense, it is integrated water management, so on and so forth. So we need to come up with some form of understanding that in Turkey, we also need to be more sensitive when it comes to the urban runoff. So these are the examples how the city can be changing the table to make the urban environment, especially the degraded brown urban environment, into a much more green infrastructure. The cities are shaped by the difficulties that they have to deal with. That is the quote from Darabont. And then I agree with that deeply because what seems to be a challenge could be and also an opportunity for a creative person or a designer. So that creative process or circular process of design starts with understanding the natural, how the nature works, the natural phenomena like carbon sequestration, what you are seeing on the left, carbon sequestration, and then just the natural system always regulates its rain runoff. And also the evaporation somehow reduces the amount of water traversing in the landscape. When it comes to the end of this journey, the fresh water, the rainwater, comes to the sea, which is a salty water, another water system, in a very harmonious way. But when you look at the central part, which is the city, without any nature-based solution, what you are seeing is the rigidity and not so flexible design with high carbon emissions, lack of permeability, a lot of sealed surfaces, and therefore the surface runoff is going really fast towards the city. So when you look at the seaside, we also have these not so harmonious but rigid lines of these coastal promenades with again a lot of permeability. So which is making our coastal environments very vulnerable. So we need to find an intermediate solution. Of course, we need housing, we need commercial entities, we need the streets, the squares, everything that seems to be impenetrable. But when we design this built environment in a nature-based focal, we can just turn the table to be more of the high quality light as we are depicting on the right image. So by incorporating the green facades and the green rooftops and then utilizing some permeable materials, even though they are looking like impervious material, they can still be penetrable. And by utilizing some nature-based cost, creating that harmonious transition is definitely possible. So the Ioannou poses as cities fighting with water if they do not adapt. So this is the image on the right is depicting a scenario how we can adapt to these changes. So what the nature-based solution relies on is the green infrastructure. The green infrastructure approach starts from a human scale and then it goes all the way up to the larger, wider urban scale and then even further to the regional scale. It involves the buildings, the streets, and then all these areas, greenfield areas that we occupy as human beings in the city. Creating resilient urban matrix against detrimental effects of global warming is possible with green infrastructure approach and the water sensitive design approaches. You can see over here, creating like bicycle friendly, not so vehicle oriented streets with permeable materials and rainwater collection, natural drainages, and then the facades of the building, and then the top of the buildings with the building materials. All of them creates this circular environment where the nature goes on and on in between the buildings and in between the elements of the public space. In the climate change era, designing water-sensitive coastal systems are equally important. How fresh water and salt water merge with each other change the city's resiliency. And we need to understand that resilience aspect, not in the sense of ecology only, but also in the social resilience. This is a social system also. What we designed is not only supporting the ecological resiliency, but also the social resiliency is important. So therefore, supporting this built environment not only incorporates what's seen above the ground, but also below the ground is intervention area. And every layer in this section always involves some form of water, even in the metro lines and then below the ground. So the supporting sustainable nature and urban connection relies on the green infrastructure and understanding water. And therefore, the Garrett Doherty calls this whole system as the quote, blue can be the framework through which to see the green. So we need to just put our blue glasses when we are looking to the green system, because the water is a driver of sustainable development, is a socio-ecological system, it is an environmental asset, it is a source and the regulator of this environment, it's a design motivation, it's a design input, and it is a design medium. So I will elaborate how these water-sensitive approaches can shape the design decisions within few world examples, real world experiences that I have a pleasure to be involved. So this is Taksim area, it's a very harsh surfaces covered with granite, and the whole system relies on the gray infrastructure, unfortunately. During the history, there are many different periods of Taksim. So just the lifestyle, the way people engage with Taksim area changes constantly until nowadays. So there is this social fluctuation and then this human topography, what we call is changing significantly, not only the natural topography, but the Taksim or our international gas. This the translation, the meaning of Taksim is the water division. It is just bringing water together and then dividing it to the neighborhoods of Istanbul, of Beyoğlu. So that's the name is taking its title from the Maximum building, the water division building located in the heart of Taksim, where we don't notice it today, but it is there. So our project redefines the scale of the open space and adds important public functions to improve the richness and the plurality of the use. Along the new border, horizontal volumes provide new public cultural services and users to guarantee a lively space during all day long. So we were not only promoting this livelihood of the activities, but also creating this urban environment which can capture the carbon more than the whole Taksim area, this built environment is releasing. So the project redefines the scale of the open space and adds important public functions to improve the richness and the use. So, and what we did was we measured the carbon situation and in how many years with this ongoing situation, Taksim will be a climate positive, which means that we'll be able to capture the carbon then it releases. So the calculations gave us more than 10,000 years. So it was almost like nothing. But our design, we was able to reduce that down to the very significant, almost like 8 years. So what we did was, in order to reduce this one, we utilized the water. We use water to explain the identity of the space, which is the Taksim, the confluence of the water. And we proposed a scheme in the park saying that, okay, even though we have to create these impermeable surfaces because this is a square and we need to protest, we need to cheer up, we need to celebrate, we need to express our feelings, and we need to socialize. So millions of people will be there. So we need an impervious area somehow to hold all that people. But then the park right adjacent to that impervious area could be the hub of the water collection. And then with that water collection, we can also regulate the carbon sequestration. So we calculated the volumes of the rain for every month, and we created this water reservoir area where all the surface runoff will go inside. So let's say in the rainy season, which is January, this whole area will be covered by the water. But when it comes to July, which is the lowest season, that water will be inside of this pool that we are creating as a reflection pool. So that's kind of like paying an homage to the people, because the Taksim is also the area we express our strong public feelings. So that is kind of like a reflection of our feelings to the water in a more positive way. So this is the plan. And then this is the outcome of this whole measuring of the carbon, measuring of the runoff. And this is the winter situation when the site will be covered with the water surfaces because we have a lot of rain, and then we just adjusted the size of this water surface to keep the water, again, coming from all the impervious surfaces. When it comes to the springtime or the less rainy times, the water will go down towards the main area, and then we will have a meadow, which is a wildlife meadow, which holds carbon more than anything. It's kind of like a wetland type of situation. But when it comes to summertime, we will have this dry meadow where people can utilize it for summer activities, for some watching movies, maybe, for cleaning up or enjoying the weather, the hot evenings in Taksim area. So we had also propose some light structured buildings, which educates people regarding the water cycle and also regarding the biodiversity in the Taksim area and in Istanbul. So the material-wise, the material language also takes its reference from the water, traditional water structures. In the Ottoman times, when you visit all our historical heritage, you will notice that there are different types of stones, the marbles coming from different geographies of Istanbul in Anatolia, expressing the cultural diversity and geographical diversity of the country. So we utilize that same concept to do the material work on the area. So what you are seeing is like the entrances to the metro, where we have also utilizing the light and then the latest technology and sensors, which is reflecting the public's attitude in a really cheerful way, as it's like sound and light, and some sensors. So it is basically just an idea, just a concept of like today, if you visit Gezi Park, you will notice that there is this boarding playground sitting on the area where we place our water collection units. So the benefit-wise, I think we could utilize the land much more efficient way. So this is an implemented project. This is a site where we are dealing a lot with the urban heat island effect, where all the grounds are sealed and the buildings are getting heat a lot because the ground is very like it's a reflected ground. It's an asphalt. It just hits the ground. The building. Like the radio economy and then the asphalt, but then we need the water collection river so that all the water will go inside, just like the proposal in Taksim area. It will go inside or not. So this is like the beginning of the construction where we have the bicycle ready on the floor, and then we are still the beginning of the construction. We just plant inside the bicycle, and then this is the thermal concrete. And then people start coming. So the social wise, why the social wise the area is starting to nourish. So that's within a month after the plantation. This is how the landscape performs in the area. So there are existing trees on the site, and then I show you the previous pictures. I am sure nobody noticed them because they were unnoticeable in that context. But with the new more more sustainable, more circular design, this whole area became more of a social hub for campus. And this is the July picture, for example, that everything is solarized, so people are enjoying this dedicated corridor under the shade of the sycamore trees. And then the buildings are utilizing this space because this surrounding area is 4 centigrade cooler than the areas where we don't have these kind of approaches. This is the winter time, and then next year the whole thing starts again. So this is before and after wave, and then at the end of the fall, water goes down to the ITU bay. And then we are using the topography to bring it to here. There are no pumps, no electricity, nothing. It's just like utilizing topography to bring it to the lower elevation, and then there is another way to fix the swale here. So that is a filter, another filter that we are putting, and then the whole thing is here as a reserve. Everything just collects here, and then we utilize this rainwater for the irrigation of the whole campus. So it's like taking again, positive wise that the water capturing and cleaning situation is really, really important and functional. So that's all I will say. What I will say as the last word is that we design our world in our minds. The way we design actually makes a huge difference. So when we design for coexistence of the people with the nature and then with the city, we need to just be really sensitive because how we design our world will determine how we will live in it. If we design without considering the limits of the earth, we risk destroying our reality. However, if we design with consciousness and awareness of these limits, we can support and sustain many lives, and that is the end of my presentation. Thank you very much.
Like Elma said, my name is Olga Ioannou. I'm assistant professor at the Faculty of Architecture and the Built Environment at TU Delft at the Department of Architectural Engineering and Technology. I'm also co-chair of the Circular Built Environment Hub, a lovely group we have here at the faculty, a cross-departmental group with more than 70 researchers currently looking into circularity in the built environment. So I was trying to, can you see my screen? While I was preparing the presentation, I bumped into this photo and I thought I'd share it with you, mostly because for me, it consolidates the very, very awkward moment we are at the moment, where on the one hand, we reach out for new green energy systems like wind turbines and PV panels, but at the same time, we are still so very much attached to our former coal consuming, let's say, activities. And this is very representative of this fragmentation, let's say, with regards to our initiatives when it comes to decarbonizing, which is a little bit of this, a little bit of that, but never a very consistent, never a systematic story. So according to our emissions, all 47.9 billion of them, scientists have found that we need to decarbonize up to 2.51 billion tons a year, which means more or less a 96% reduction. And that would require not only the use of sustainable energy production, but also what I claim in this presentation, a very systematic and systemic, rather systemic change. But we are in this fragmented, let's say, landscape of practices where instead of looking at our current consumption and CO2 emissions, energy consumption, CO2 emissions, we find new ways of tackling the issue, like carbon trading. Many countries buy CO2 emission rights from countries that produce less. And we still look into building components and energy production apparatuses like wind turbines and PV panels, where there is an increasing growth that reaches 17% and 26% for both. And while we're doing that, we also disregard the fact that these products, like the PV panels, for example, employ a massive number of materials, many of which are critical raw materials, and therefore the supply doesn't always meet their demand. And also these materials come from a wide variety of countries across the globe, which means that our decarbonizing needs in the West largely depend on mining that happens in locations other than the Western part of the world. Here with students, we've tried to map the origin of building products, materials. For example, a timber frame window that is manufactured here in the Netherlands. To their surprise, we found out how the materials that make up this window come from all parts of the world. So what seems to be a very circular decision to use a timber frame window manufactured in the Netherlands ends up being highly dependent, highly reliant on so many different locations, from Brazil to Russia to Southeast Asia. So there is material dependencies that kind of obstruct our transition to a circular built environment. There is material dependencies. Currently, there is projects in the US and China and the United Arab Emirates that require materials that are mined in one location, then transported to another location to become components, to be processed into components. And then for the fourth or the fifth time, they're shipped to their final destination to be part of, what has happened? Are you still with me?
Yes.
I'm sorry. But there's been a system. What? Can you now see my screen again?
Mm-hmm.
Yeah,
Looks good.
fantastic. And not to mention the fragmented ways of us dealing waste, distributing waste all over the world. I recently read that the EU has finally decided to not ship plastic waste over to countries like Malaysia or Indonesia and to try to process plastic waste within the OECD partners. So two major challenges here, decarbonizing on the one hand, decolonizing in the other, as a way to do this change, to make this change more systemic. And here at the Faculty of Architecture, like I said, we have this group, Circular Built Environment Hub. And with this group, we've tried to create a tentative definition of what the circular built environment is, to practically describe what we mean by decarbonizing and decolonizing, trying to enable society to thrive within the planetary boundaries by closing, narrowing, and slowing down resource loops. And what you see here on the left is the scales to aspects model we have created that represents the scales we find to be relevant for the circular built environment, shown here as being completely interlocked and interdependent. And around those scales, an equal number of aspects where we think circularity manifests in the built environment through these aspects: management, technology, design, so on. Now, one of the things that we've realized over the past years and the ongoing research is that the component scale, which is part of that diagram, is a very central, very crucial scale to the transition. Mostly because if we can think of the component scale to be crucial to the building making, as in the sense that materials and components will have to outlive the building they are part of. In a circular built environment, the value of the components, the materials the components comprise of, might outlive the very building, the form they make up for. And if we try to analyze the components per shearing layer, then we realize that even for a medium scale housing, there is all sorts of different parts that we need to consider for a building, from the facade and substructure all the way to the internal finishes and the superstructure. Now, depending on our strategy that we would like to employ to make the transition of a building product, building component towards a more circular version of it, there is a number of domains that are being affected. And talking about systemic change, we cannot make this transition unless we set, let's say, the goals, we set the ground for this transition. And those domains we've been able to identify as being super relevant for the component scale are the domains of materials, design, manufacturing, and management. And here, of course, I have this slide about setting goals, about making decisions with regards to the strategy we have in mind, to either use more biological materials and to refuse the use of technical ones, or to even refuse the use of the component in the first place, all the way to creating tools like digital twins, of course, and material passports to help monitor and maintain properly a component to prolong its entire lifespan. But how can we make these domains more operational, right, with regards to how we teach about circularity, but with regards also to how we research about it? So we've turned these goals into questions, and then we've developed what we are sometimes referred to as the circular building product canvas. And the canvas is composed of these 4 domains, and it comes with lots of questions that either our students or researchers need to somehow address with regards to making more circular building products. And of course, these relate to the origin and the nature of the materials used, but also the interfaces of those parts within a product, or the interfaces of the product with regards to how it's fixed on the building, but also how new technologies like additive manufacturing, CNC milling, and robotics can be currently employed to transition to a more prosumer, let's say, kind of user, who's more of a doer, someone who can actually have a lot of interaction within the activity of manufacturing the building product itself. And of course, the domain of management that looks into all these hidden systems, take-back systems, or maintenance systems, or reverse logistics systems that can help, like I said before, prolong a product's lifespan and allow for a second and third use in the future. So through these questions, our students and researchers are ultimately asked to inquire on how building products are made at this moment, and therefore they are required to analyze existing building products like the ones you see here, from windows to sandwich panels to each-on blocks, the way to further developing their ideas about how these products or parts of a building can be redesigned and reconceptualized as being more circular, having a more circular potential. And here you see different ways of delivering slabs or complete structural systems where load-bearing walls with hemp-grade timber, or to create new integrated design facades like this one here, where students need to identify the different layers within this facade and also identify the challenges of making it as circular as possible. The challenge is also reusing building components to produce new forms, and therefore engaging in design for disassembly approaches, but also using materials in unconventional formats like bricks to create new arched slabs, for example, or by minimizing the impact of waste. There's also students looking into how waste can be turned into a resource and then aesthetically be upgraded to producing something that, even if it's flawed, can create a new architectural vocabulary. And there's students at a higher level in our school, let's say at the master's thesis level, who are now looking into completely new products, bio-based. Here you see an engineered biocomposite that not only is 100% bio-based, but it can also be formed, reformed, and deformed again multiple times, thus prolonging its lifespan. There is research currently on manufacturing techniques to minimize the number of molds needed to produce complex geometries. And here, the student has looked into this project using a bio-based material and has designed the facade element in such a way so as to indeed minimize the number of molds needed without jeopardizing the complexity of the facade. There's students looking into biodiversity and how to integrate reused materials into cladding, also integrating biodiversity on it, also allowing for an easy disassembly that anybody can do by themselves. And there are students that are currently looking into timber top-ups. There's been a recent policy here in the Netherlands to increase the number of timber top-ups in the country, also to increase the number of housing units created. And therefore, students are now looking into the possibility of structurally adding more floors to existing buildings, and what would the right balance between deconstructing part of the building and adding new floors to it should be. There's also students looking into waste, waste produced by wind turbines in this case, making new structural systems out of blades that are no longer in use. So instead of landfilling this waste, creating crucial structural systems to integrate it in. And there's also students looking into digitalization and ways of making decisions about reused steel components in this case, based on their physical dimensions or properties. I mentioned critical raw materials before. There's also a very systematic attempt to map how critical raw materials are integrated into facades and building products. Here you see the findings of a student who looked into the existence of critical raw materials in aluminum carton walls. And of course, some of them are also interested in mapping the very fluctuating, changing landscape of stakeholders that are now involved in reuse value chains, like this student who's been systematically trying to map how many new professionals we need to transition to a reuse process, a process of reusing materials, secondary materials from deconstruction projects. And she identified the number of professionals that are needed, as well as the different expertise they should have in order to enable this transition. And there is a number also of ongoing research projects with regards to facades and building components, and that is one of them. Juan has recently completed his PhD research, I think it was last June, on facade leasing. This is one of the most representative projects with regards to how systemic the change is. This was a pilot project that was implemented here at the CITG building, the building of the civil engineering faculty. And in that building, they tried out renovating one of the facades of the building by not buying a new facade, by leasing it from a company. So the company had to develop all these new models, retain ownership of the facade, and then a lot of new ideas and concepts needed to be in place, financial, legal ones. And then this research further highlighted how important it is to look at these things, not only from a technical and technological point of view, but to try and understand and, let's say, uncover the complexities that lie underneath the technological challenges. There's also ongoing research with regards to timber. We also have a new timber professor here at the faculty. This is in particular, a PhD research looking into ways of changing the dimension of timber joints by using humidity. And there's also an ongoing research on the social aspects of circular transition with regards, again, to building products and how communities gather around specific needs and co-create products based on resources that are directly available to them. We tried to map this complexity of transitioning to, let's say, more circular building products, and we came up with something looking like this. And still, that is an abstraction. I think it's much more complicated than what this diagram implies. The realization is, however, that there cannot be a transition to a more circular building product market unless we uncover those domains that I mentioned before, but also their interdependencies, and we make these interdependencies equally important to the products that come out of them. Therefore, a complete reversal of the rhizomatic system, like I started and ended this presentation, showing that the process is as important as the product, and unless we actually address the complexities and the challenges of the process, we can never come to, let's say, a wider dissemination of products with a higher circular performance, with a higher circular potential. And we will remain fragmented, just like I've shown you in the first picture before. Like when we produced something, and maybe that is of value, but it's just a drop in the ocean of what is otherwise a major transition. Thank you very much.
Hello, everyone. Thank you so much for being here today. Elma, thank you for introducing me. My name is Ajla Aksamija. I am a professor and distinguished chair of Resilient Places at University of Utah. Today, I will be talking about regenerative design and achieving net zero energy in existing buildings through energy efficient retrofits. When we look at the circular economy, decarbonization plans, and the effect of existing buildings, what immediately comes to mind is that buildings are responsible for more than 40% of global energy consumption. They're also significant contributors to carbon emissions. For example, in the United States, the majority of existing buildings were built before 1970s and even before the first energy codes were implemented, which means that they are outdated, not energy efficient, and it is extremely important to consider the concept of existing buildings within decarbonization and how can we improve their performance, their energy performance, human comfort, and also how to retrofit existing buildings to be carbon neutral or net zero energy buildings. When we talk about regenerative design, I would like to define what do I mean by regenerative design. So regenerative design can be defined as a design approach for existing buildings, which considers comprehensive, sustainable, energy efficient, and resilient design methods. It can be perceived as exploration of buildings' functionality, aesthetics, human comfort, and energy performance. In terms of regenerative design, this is completely different than historic preservation, which means that we need to consider building function, possibly change the building function, let's say from commercial into residential, from residential into some other building typologies. And also we need to consider adaptive reuse. I believe that globally, the pandemic has showed us that office buildings became, not usable for a few years. So how do we consider building aesthetics, building function, energy performance, human comfort, also size? In regenerative design, we may or may not use original materials, but we need to consider holistic, comprehensive approach to improving the building performance. In terms of sort of resilient design methods for new construction as well as existing buildings, I typically like to talk about basic design methodologies. We always need to start with passive design techniques, considering building climate, orientation, thermal performance, shading, daylighting, natural ventilation, and really try to maximize passive design techniques before moving on to advanced building technologies or renewable energy systems, because those are smart ways to design buildings, but also because of relative cost. passive design techniques do not cost any money, or they have relatively low costs compared to some of the advanced building systems, energy efficient HVAC, lighting systems, and so on. So we started passive design techniques, maximize their application on particular projects. Then we look at advanced building technologies, energy efficient lighting systems, energy efficient HVAC systems, and then renewable energy resources. So this is the only way to achieve net zero energy in existing buildings, because if you simply start by renewable energy systems, we're completely missing the picture. I often, in my professional practice, clients who are interested in improving building performance start by stating, "Oh, I would like to include renewable energy resources." That is not the right approach. This is the only way to really achieve. Integration of building performance analysis is crucial during the design process and during the regenerative design process, because we constantly need to check the impacts of our decisions. Let's say different passive design techniques, daylighting, shading, improved thermal performance. We need to quantify the impacts of those design decisions on building performance, and then advanced building systems, energy efficient HVAC systems, because if you are not integrating simulations and modeling in the design process, we simply don't know what we are doing. We do not know what the energy performance would be. So integration of building performance analysis during regenerative design process is crucial. Also, in terms of advanced building technologies, it is currently possible to achieve net zero energy in existing buildings as well as new construction, but we always need to consider, first of all, costs, as well as benefits and risks. And integration of building performance analysis when we're analyzing advanced building systems, such as different types of renewable energy systems, photovoltaics, wind turbines, biomass heating, advanced facade systems, advanced HVAC systems, for particular sets of constraints associated with single project. We might have specific benefits as well as risks that need to be considered. And again, integration of building performance analysis can help us make educated and best designed decisions that we can make. So now, because we have limited time, we have about 15 minutes for each presentation. I would like to be very brief and present you a case study. This case study is a regenerative design for net zero energy academic building located at University of Massachusetts Amherst. University of Massachusetts Amherst is located, let's say, 150 miles, 200 or something kilometers west from Boston. So it's a heating-dominated climate, east coast of the United States. UMass campus is fairly large. It houses more than 30,000 students. And this is the campus map. The Hasbrook Hall that we took as a case study to investigate in this research is located along sort of the eastern edge of the campus. What is interesting about this particular building is that the original building that you can see here in orange was built in 1947, and the addition building that you can see here in purple was built in 1974. So both buildings serve as a research laboratory building and academic building. So the building includes auditorium, classrooms, as well as research labs. What is also crucial is that the building is, so this is kind of the main pedestrian path as well as main circulation path through the campus. And currently, the building is used by pedestrians to connect east part of campus to the west. On this side, the building has 2 or 3 floors. On this side, basically, there's one level change. So students, faculty, staff, they walk through this building to access the western part of the campus. Building that you can see here is a high-rise campus center, student union, administrative building. So it is like a central location of the campus. And our sort of challenge was to consider the existing conditions of the building and see how we can improve building performance with regenerative design. So we first looked into climate conditions. We wanted to determine right passive design techniques, so understanding shading, orientation, daylighting. I mentioned that on the western side, there's a high-rise building, relatively close. So we wanted to understand the shading potential from that building, as well as solar exposure for potential photovoltaic array on the building rooftops. So analyzing climate and passive design techniques is the first step of the process. Then we analyzed existing design conditions. We looked into existing construction documents. We also conducted observations to see how the building is used by students, faculty, researchers, and so on. What is interesting to know that on the addition building, there are essentially no windows. There is a glazed part on the first floor, but the research laboratories they're completely enclosed. So built in 1974, I'm not really sure what the design thinking was, but no daylighting whatsoever. Also, there's no insulation in exterior walls. On the original building built in 1940s, there are existing windows that are single glazed. Currently, students are using aluminum film or plastic film to protect the building in the wintertime because it's quite cold. The circulation is not circulation through this place that I said to the western part is not very easy, not accessible. And there are also a lot of code issues that, compared to current code, the building does not currently meet. So we looked into existing orientation, existing programming, existing planning, the use and functionality of the space, and proposed a better and improved regenerative design strategies. So this axonometric shows regenerative design strategies that were used. So improvement to the original building built in 1940s included spatial reorganization. In a minute, I will show you diagrams and floor plans that you can see. Opening up classrooms to provide more daylight, adding photovoltaic array on available rooftops. The addition building that was built in 1970s, providing windows to interior spaces, also reconfiguring research labs so that they do have access to daylight and changing the circulation through the building. And then our design approach for the atrium and classroom, the building was to demolish the existing conditions because they're not functioning properly and they're not up to code, and providing new collaborative space, these two interesting forms, and improving the circulation through the building. So this would be a new 5-story atrium connecting the two buildings, but also connecting the campus, including regenerative design strategies, renewable energy sources, providing a green roof and a garden on a rooftop of this particular building, and improving accessibility of the building and improving the building envelope. So here are the diagrams that show different levels and improvements in terms of circulation, reprogramming. So we pushed research laboratories to have access to the daylight. You can see here circulation through the atria and connection to the campus. We also modeled energy usage of the building with the current design. Then we compared to the actual energy consumption data of the building. And then we also conducted energy modeling of retrofitted or improved energy consumption. So the initial simulations gave us EUI, energy usage intensity, of 139 kBTUs per square foot. I'm sorry that this is in imperial units. The actual EUI was a little bit higher, 154 And always we have to take results of simulations and modeling with a grain of salt, right? It's highly unlikely that we will get 100% correct simulations. And then when we improved the building performance with the retrofit design strategies, our EUI was 126. We also conducted thermal imaging of the building facades. As I said, the winters in northeast part of the US can be quite cold. So this shows thermal imaging in January. I mentioned that the additional building built in 1970s does not, it's basically just concrete and brick facing. No insulation, no windows, very poor performance. And then on the existing building built in 1940s, there was some insulation and exterior solid walls, but the windows were pretty problematic. So then we took a closer look into building facades, components, existing conditions, and redesigned building facades to be more energy efficient, including addition of insulation layers, providing high efficiency windows, and also including solar wall systems that are kind of passive design technique for preheating air for heating systems, and including one of my other research projects, a smart facade system called thermal-electric facade that integrates smart materials and based on temperature gradient between the inside and outside can generate heating, cooling, or electricity for interior usage. So you can see here details of the facade components, respective R values, and investigation of thermal performance. We also analyze heat transfer in windows, framing, condensation potential, and here's basically redesigned system and addition of new facade to the exterior. We also performed, so the issue was, where do you place the insulation, on the exterior or interior of the wall system? The question is, what about the condensation potential? So we also performed simulations and modeling to understand hydrothermal behavior and solid facade elements. So these graphs and charts show dew points and calculations for condensation potential in original facade systems, as well as redesigned and readapted facades. And this is a diagram that shows sort of a holistic improvement to the building and all of the different design techniques that were considered. So as I said, the atrium was the main component that was added to the building. You can see here how the circulation was improved, and an atrium was included as a design strategy to connect the two buildings and also provide collaborative spaces for meetings, collaborations, and so on. The major sort of passive design technique was to improve the building envelope performance by adding insulation layers, solar wall system, thermoelectric facade where possible. And then in terms of renewable energy resources, including photovoltaic panels on the rooftop, but also PV glass in the atrium where appropriate. Triple insulated glazing systems for windows, fuel cells as another renewable energy resource. So you can see how relatively sort of typical research laboratory building that can be found on this particular campus or many other campuses across the US and also world can be analyzed, retrofitted, and regenerated to improve energy performance, human comfort, and meet the net zero energy goals. So a few concluding remarks. We talked about the importance of existing buildings and regenerated design of existing building within the context of decarbonization. As I said, majority of the buildings in the US as well as globally were built even before the earliest energy codes were implemented, which means that they're not efficient And in the future, we will have to start looking into existing buildings and ways to improve their performance, functionality, as well as energy performance. It is necessary to consider comprehensive methods for reducing buildings' energy consumption, adaptive reuse, functionality of the building, as well as renewable energy systems in these retrofits. And the last thing, because we're running out of time, that I would like to mention is that achieving net zero energy goals in retrofits with available technology is challenging, but possible. Also, one other important aspect that's based on years of research is that on larger complex building types, such as research laboratories, it is extremely challenging, almost impossible to achieve net zero with just one renewable energy system, such as photovoltaics, because we typically have limited roof area or limited site area where we can include them. So we typically need to include a minimum of 2 or more renewable energy systems to achieve net zero energy goals, but comprehensive design strategies that look into passive techniques, reducing the energy consumption as much as possible, then advanced building systems, and then renewable energy systems is a way to go. So with that, I would like to thank you.
IT colleagues invite me to give a talk about bamboo-based composite materials. And last year, 2022, we worked together successfully secured this British Council project, and then it's my honor to host a visit for the delegation of my team to Edinburgh University. And then together we built some small bamboo timber bridge model in there. So we hope next year and later on many so we can maybe continue the workshop in here in Istanbul. So sorry for maybe skip the poster design. So my topic is on the bamboo-based composite structures as well as composite materials for construction. And then hopefully I'm looking into the developments of bamboo timber composite and bamboo composite beams. And then my background is structural engineer. And then, I'm both looking into the circular design and the sustainable materials from different angles. So, before we go into the details, I'd like to maybe talk about what is the opportunity, challenges, and then for our maybe civil engineering and construction industry. So as we all know, the construction industry accounts for 30% of the CO2 emissions globally. And then the decarbonizing construction building a new net zero industry plays an important role in achieving the UN's sustainable goals. So by to fighting this challenge, and then the construction industry now are kind of have a chance to move into the bio-based construction. So mainly, I think we begin the bio-based construction, mainly the timber industry, timber constructions. So when you look at the timber construction compared to the concrete steel, we can immediately notice in terms of the material strengths that are different. So timber has a lower strength than the steel and concrete. So because of this one, using the timber construction, we notice that we have a very small opening. Say, for example, if you want to create a large opening in timber construction, timber housing, you possibly need support from the steel and concrete material. And also, timber natively will have a slightly weaker floors to create vibration, excessive diffractions, as well. And also the timber buildings tend to be a small frame. And compared to the tall buildings, we notice that the tallest timber buildings are small, very, very small. So there are a lot of room for us to develop. So for timber industry, what they need for this one, so they work from our understanding, that they need a strong bio-based composite materials for construction. Also, they need technology to further enhance this composite of these new materials. So we are developing some of the technologies in mind later on. Also, the design method for the engineer, architect, adopt these new materials, and also create the know-how and the market production process for creating these materials. So then this also provides the opportunities for us as researchers. So how can we provide assignments and user assignments? Again, the bio-based production materials increase the market share of the simple industry, and also develop technology to further enhance this material. And also we can develop the supporting service and toolbox to support them to conduct the design. And for the us, we can also maybe using this knowledge and this new idea to secure large size of research and development fund, and then also create a spin-off companies as well. So this is the challenge and the opportunities for the researchers. So then people will ask, okay, there's a lot of different types of bio-based materials. Why you choose the bamboo? And also later on I mentioned why you choose the composite for bamboo. So why you choose the bamboo? Because the bamboo we are using in this research is not the raw bamboo, it's not a circular bamboo farm, it's actually an engineered bamboo. So the bamboo is split and plant into a long slender strip that glue them together to form this timber lumber strip of material, and then you can use as timber. So for this engineered bamboo, they have very high strength compared to timber, and also they are light. So that's why you can use it quite efficiently, and then they are low cost. And bamboo is famous for the poor man's timber in the past, but now it's not anymore because they can create really beautiful structures and even for commercial or high-end use. And why we use those material? Because with combining the bamboo and timber together, we can create a lighter but stronger material, and then we have a better structural activities, less vibration, and then a better acoustic insulation, because we have a layer of bamboo and timber, the stiffness change, so then when the strong wave transmits through these different types of material, the attenuation will be higher than a single material. That's why it's very useful for acoustic insulation. Also, combined with the timber, then we have a simpler joint connection, use existing timber connections as well. And then the bamboo and timber, the native roots align each other. So the experience of the bamboo composite are beautiful, and then this is what architects they want the beautiful material. And then also because we combine these two together, in European continent we don't have the native bamboo forest yet. Sorry, not native bamboo forest. But however, somebody have found in the bamboo forest at the moment, hopefully in the near future, these European grown bamboo materials as well. So, but combining this together, we can use quite a lot of the low grade that European timbers, and then to enhance enhance the added value of the material. And also combining together, we can have a chance to build that large frame structure or overbuilding structure. So we have to give some attention to these materials, and I will go over here. So in June this year, our students and then a group of Chinese students, we built these structures to in Spain, in China. So this is some of the many photos that we took in the construction and after the construction. You can see actually combining together, they have a potential to create large size structures. And also, when we combine them together, you have potential to use fast growth soft wood in the UK or Europe. And then by doing that, supporting the carbon neutral construction. And so in our invention, so what we invented composite frame system. So we use this composite beam and column and to hope we can create a new frame system for this for the new building design. And then we developed ones that pre-stressing technology. I'm going to briefly mention it today. And then for this technology, we enhance the composite effect. So, and also we can then using the existing fixings from the timber industry as well. So to enable us to do that in nature, our research team are developing the technology or knowledge from the fundamental to application level. So in fundamental level, we look into the small scale sample test to find out material property and then to develop a design. But I will simple and practical constitution model for bamboo and timber together. So that small photo showing the curve there, we are still modifying and still improving this constitution model. Then we apply this model to the new bamboo timber composite for the analysis and the computer programming as well. So in practical level, and what we did is that we built a different type or manufacture different type of the bamboo timber composite, and then with a different layout. You can see some single layer and then some double layer semi-beam. And then also we look into the ratios from the laminated and timber ratios, what their impact to the strength of the structural maintenance we create, and we compare with the traditional blue beam as well as in our study. So doing that, we also conduct one of the trial productions in China in 2021. And during this conduction, we also proposed a new concept for pre-stressed composite for bio-based material, because we believe that we didn't need like a steel or maybe the other potential chemical related carbon fiber bond to achieve the stress, and because they create stress compensation, they also use the non-technical materials, and then because the stress compensation, they create a large stress in the small area, it tends to have a large maybe the stress relaxation. So to do this exactly what we can do is actually we can force laminate the different components that were typical and different with the different architectural different geometry properties, like if they have a different curve or different lengths, and then you force them together. So once you release these press, and then the parts will interact with each other to create a pre-stressed state inside the member itself. If this pre-stress is counteracting with external load when you apply, then you maybe get a benefit. You can increase the strength. Also, we can utilize materials more. And then so every material can the average stress better. So this is how we did, and then we also prove this technology is scalable. We can use it. We can use this what we call the existing that industry facilities, slightly modify the what we call the expression technology, and then we can achieve these features manufacturing quite easily.
Okay.
So yeah. So we also conducted that is investigation on these materials, and then we got some interesting findings from our care. As you can see, normally these are symmetric structures, and then but however we noticed that in our previously the curve, the constitutive curve we produced already, the tension and compression for bio-based materials behavior are different. So they create some of the very interesting effects you can see from these figure A is there. The figure A and B, so you can see that the tension and the strength, the tension and compression by the difference. And then so there is not so much that the loading you can have. And also from the figure C, you can see actually during the loading, the neutral axis, when we analyze the structure, they shift and move. So all our now current that model analysis structure didn't consider this one. So in our future analysis, we need to incorporate this one into our study. So in the last photo, you can see from there, you notice that the black one is actually the timber. So the other line, there's a longer leg in there. There is a sandwich beam with the equivalent size, and then with the bamboo timber in top. Then you can see the strength nearly double, and also they have a longer span in plastic stage, so they have a better activities in the structural performance measure. And if you double the ratio, you double the laminate bamboo layer, you can have much higher. So that you can see that two green lines in the figure thing, they are much stronger and then higher strength. So this structure. Then I have a few interesting photos of political institution. It's supposed to be like show you the last moment before the structure is broken. So maybe we can that's the moment where the structure is broken. As you can see that there's some interesting finding we also find out. It's the first time we recorded. You can see the top photos in there. While this structure fell, and then you can see a very interesting curve in the top of the beam next to the loading point. So the timber and bamboo is actually the curve in this level. So this is the elimination in the compression zone. It's very interesting. In fact, we have to look into why it happened, how it happened. So, and then also by doing that one, you can see the bottom. Normally they will fail. The first fail will be the top and then in compression. But after that, and then the bottom, the tension level, so pretty fail. So this is some effect we find out there. So the key finding from our one is that we prove that this effect technology can be scaled up using the industry facilities. And then also we look into the different failed categories and also connecting this failed mechanism to the layout of the cross-section, and then the parameters such as the laminate and timber linkers as well. And also we do an in-depth component analysis using all the data we gain from the strain gauge or the other measurement facilities. So we have concluded several new assumptions for further study. The first one, we confirmed that the plane remains plane section, which is fundamental theory for the clinical analysis. It still remains plane. It is still valid. And then the cross-section, the neutral axis, they move during the loading in different stage. So these need to be considered in the further analytical or numerical analysis. So the last one, the actual stress and strain from the composed materials, you can combine stress stress together with the stress caused by external loading together. This is accurate. So this is a superposition. You can put them together. So it's we call maybe a principle of superposition as well. So this is the bamboo and timber. So very brief, just run through this because of time, and then the bamboo composite beams. And then why we use the concrete? Because we notice that for the bio-based materials, compression compression strength is always lower than tension. So we want to use maybe a layer of the concrete to enhance their strength compression, and we also want to look into what will be the impact if we kind of curve the bottom bit a little bit and build an arch effect going to increase the strength or not. So we have some interesting findings here. So, and finally, we developed this one case. We guessing that the interlayer between the concrete and the steel, the slip interlayer slip is one of the key factors to monitor. So that's why we developed a new technology, a simpler technology to monitor this effect. And then by doing that, what we can do is that we can put in the LED between the two layers, which you can see from the photo there, to measure the interlayer space. So that when these timber and then when these bamboo and concrete, when they move, and then this LED can measure the deformation. And also we put a strain gauge in the middle. So that might be not very low structures. We want to find out that actually the LED, when they move, they can predict what is the strain inside in the middle space. So they should match each other. Because we put the strain gauge in the between the layer of concrete and the layer of the bamboo as well. So this strain difference will tell you how much the strain change in this one, but this one can be predicted using the strain gauge rather than using the LED rather than the strain gauge. So this is what the development we have done. And then, so I talk about the detail of the and like that similar to the community. So I think the design parameters for the both type of the linear straightening and the curving is the different. So this is the test setup and also some of the findings here. So one of the very interesting findings we find out that is actually the dark connection, these mechanical laminate structures, they are actually not effective, but not very effective, because you can see in very early stage the deformation along the beam. This is in the figure 8 during that one. So they actually even out, they actually deform at the same position. They level out. So all the deformation in the beam, between the concrete and the what you call the concrete and the bamboo, they actually move together. So which means the interlocking effect is not behave very well. So also we can notice that from the strain reading and the difference between the strain, the jump between this gap, they start very early at very early. And also when we analysis this structure, but this structure is quite reasonable because you can see the blue area in the figure C. And the slope under and slope above is actually profile if you have a fully composite effect and or in series analysis or with a non in what we call the composite effect, what is the strength looks like. So that our test is in between this one. So that's actually quite reasonable result. And also for this, the last figure we can show it there, you also notice that actually the neutral axis is moving all the time when the loading because of the mechanism. And then the fail in the interaction they develop progressively. So in some stage, the strength will come back and move and so this is some very interesting information. Also, we noticed that if you use the LVDT figures that we've been showing in there, so the blue color is from the strain gauge, and then the other orange color, the small photos, is from the LVDT. So we combine the top of the large photo, we combine this LVDT figure from all the samples, the average them out. So this middle line, the green line, match the strain gauge measurement very well. So which means we can actually use the strain gauge as use the everyday measurement to predict the difference of the strain. So this is some interesting method we can develop in the future. So we also classify all the fail mechanisms. So the main mechanism of all this one we find out no matter straightening or the curving, the fail mechanism is actually the shear failure between the laminated layer. They fail in there. So once that fails, is a sudden failure, it's brittle, and once that happens, and then the beam is split into two beams, and then they fail instantly afterwards. So this is the key one. So that's why conclusion including that no matter what we increase, you not increase the shear strength of the laminated beam, you won't be able to achieve the higher strength. This is one important. very important. So we need to sort out that one until you develop efficient system. You develop use time when people use it. And finally, the method we use in the ability to measure this the layer split is much efficient than the spin values. So that's my start. Thank you so much.
Thank you very much. I think I was just told that we are running out of time and we'll not have time for questions now, but we'll do that at the end of our symposium today.